This is called limits at infinity, and we're recording. And horizontal asymptotes, and you already learned, look, to infinity and beyond. There's what I thought I'd get whoever learned. Okay, so limits at infinity and beyond, and horizontal asymptotes. That's what this is all about. So if I have this graph, which I stole, right, which I made this one, don't tell anybody, but I made this graph. If I see this graph right here, and I were to draw in a line right here, it has an asymptote, and it has an asymptote kind of right going through there like that, right? And this graph has an asymptote at, what is the equation of this line? What's the equation? Y equals -1. So it turns out that a horizontal asymptote and the limit as x goes to negative infinity and to positive infinity are the same thing. Okay, so what all this says is if a function, if f is a function and L1 and L2 are real numbers in the statement, this means the limit as x goes to negative infinity, which is different than the limit. We have limit of infinity, which we'll talk about in a second. That's when you have a vertical asymptote. But we also have limits at infinity. So as x gets very, very large in the negative direction, this thing approaches -1. Now, does anyone remember the rule how you find a horizontal asymptote? How do I tell that I have a horizontal asymptote there? Chad?
It's like you factor, like you can cancel it out and still horizontal asymptote.
Yeah, but yeah, if you could cancel it out, you have a horizontal asymptote there. But also, no, that's a vertical asymptote.
Oh, it's what the denominator can be.
Yeah, not quite. Yes, sir.
Because there's a integrate, you just do the
Okay. Right. So what Francisco said, now I'm going to say that in English, okay?
Thank you.
So what he meant, okay, is that, remember this rule, if the degree is the same on the top and the bottom, remember that? Got it? And then you have a horizontal asymptote that is the ratio of the coefficients of the highest degree term. So this, you're gonna see a slide in a minute, but so the coefficient of this is -1, and the coefficient of this is 1. So the ratio of the coefficients is -1. So you will have a horizontal asymptote at y equals 1. So this is read, the limit of this as x goes to infinity is equal to positive. The limit of f of x as x goes to infinity is -1. The limit of f of x as x goes to negative infinity is also -1. So in this case, for this function, it'd be -1 in both cases. Or again, I'm going to give you a couple more examples. All right. So this means if the denominator, if you have a 1 on top or any constant on the top, for that matter, if you have something with an exponent on the bottom, right? And if you have something with the exponent, you're going to negative infinity. The limit as you approach infinity is going to be 0. Okay. So in this last function, what happened in that last function? Where were we? How do I go backwards? Let's just go right. All right. Can I go backwards? Yeah. So in this last function, that's not quite exactly the same as this. So if I just have like a rational function where I just have a constant on the top and something with an exponent on the bottom, the limit is always going to be 0. But you could use that to talk about limits of more complex functions. For instance, okay, say I have this function, where's my function? Limit, say they ask you to find the limit of 3x to the fourth minus 5 over x to the fourth as x goes to infinity. I'm not very good at drawing infinity. I get better at it though, as I go. So what I could do with this is I can rewrite this as the limit as x goes to infinity of 3x to the fourth. You're allowed to break up fractions like this over x to the fourth minus 5 over x to the fourth. Do you know you could do that? You can't break up the bottom with a fraction, but you can break up the top into two separate fractions, right? It's like 3/5 plus 1/5 is equal to 4/5, right? So I'm breaking it apart. This I can reduce, okay? What does this reduce to? What can I cancel out from the top and bottom? I can cancel this out. So what I'm left with is that's equal to the limit of 3 minus 5 over x to the fourth. And using this rule right here, what does this thing go to? What's the limit of this as x goes to infinity? 0, right? This thing goes to 0, right? Because as this becomes infinitely large, this thing becomes infinitely small. And so my limit as x goes to infinity of this function is equal to, is just equal to 3.
I adjusted the rule and did it.
Yeah, I know. Yeah, so what Francesco said is, why can't we just use the rule that we did not? You can't, okay? So I don't care how you do it. So what he said is, if I look at this function, right, it's the same as the rule for asymptotes, right? They're just talking more about, but the degree of the top is equal to the degree of the bottom, right? So you just compare the coefficients 3 to 1. So the ratio of the coefficients is 3 to 1, right? So the limit, you could just do it that way too. That's the easier way. So the limit of this as x goes to 0, x goes to infinity is equal to 3. What's the limit as x goes to negative infinity? Same thing, okay? The same thing is equal to 3 as well. Okay, so it doesn't matter if you're going from the left or the right, you're going to get the same value for the limit. Okay, questions about that? Well, no. Okay, so let's move on then. So here's the rules of asymptotes. So these are the rules these are the rules of asymptotes that we're now applying to limits. Okay, so all this says is consider rational functions. So a rational function, for example, would be something like 3x to the fifth minus 4x cubed plus 2 over 6x to the fifth minus 7x to the fourth plus 1, right? So this is a rational function. F of x is equal to this, okay? I'm just making things up, okay? Where this is a polynomial, so this is a polynomial function, meaning you can't have any fractional exponents or negative exponents or anything like that. And this is a rational function. And the limit as x approaches negative infinity is as follows. And this is exactly the same as the rules for asymptotes. If the degree of the top is smaller than the degree of the bottom, as in 3x over x cubed, okay? The degree of the top is smaller than the degree of the bottom. That's because this is the bottom function, this is the top function. Then the limit goes to, the limit is 0, right? In other words, you'd have a horizontal asymptote at 0, if you were to graph that, okay? This says if the degree of the top is equal to the degree of the bottom. If this number is equal to this number in the highest degree term, then you compare the ratio of the coefficients. So that's like this case up here. So what would be the limit of this function as x went to infinity? M is the degree of the polynomial, okay? And the top polynomial, and N is the degree of the bottom polynomial, okay? So, what was this approach? That's right, Dan, what did you say? 1x, right? So the limit of f of x as x goes to plus or minus infinity, right, is going to be positive 1. And the last rule is the same as it was for asymptotes. If the degree of the, except in this case, we know we're going to have to find the slant asymptote, which we had to find before. So if mn is bigger than m, in other words, if the degree of the top is bigger than the degree of the bottom, the limit does not exist. So if you have something like this, limit as x goes to plus or minus sideways 8 of 3x to the 7th minus 2x over x to the 6th is dne, right? So the degree of the top is bigger than, that's all that means, okay? This is English. Why do they make it like what? Because they're mathematicians. Yeah, they're not like high school people. They don't need to explain it to the layman. Okay, you got that, Evan? Good. All right, let's move on then. Do I have more examples? Oh, I had some more examples. Well, you got some good examples. Oh, ooh. No, you could do that with any. I don't know why they do that. I'm not even going to do it. Limits of rational functions, we talked about that. Here's a word problem. This is kind of fun. Who's in the business? All right, let me get who's the business. FBLA or DECA or something. No one in here? You are, okay? So here's a business application of a limit, right? And so what they say are your manufacturing greeting cards for a cost of 50 cents per card produced. Your initial investment is 5,000, which implies that the total cost of producing cards is given by this, right? So if I were to produce 1,000 cards, right? So you plug in 1,000 in. How much would it cost me to produce 1,000 cards? What's 1,000 times 50 cents?
5,500.
Right, that'd be 500 plus 5. So that'd cost you $5,500 to produce 1,000 cards. This equation gives you the average cost per card. So if I divide that by how many cards I produce, so this is kind of question A over here, right? If I divide that by how many cards I'm making, in this case 1,000, how much is each card costing me? 5. What's 1,000? 5,500 divided by 1,000? 1,000. $5.50. Okay. So if you produce 1,000 cards, it costs you $5.50 per card, right? Is that a lot? That's kind of lot, because you have to have a high markup. This is why if you go, that's why you want to go to Costco to buy your groceries. You know, because the more they sell, the less they have to charge for stuff. You know. So let's see an example. I'll show you. Okay. So if you produce 10,000, because this is your setup cost, right? So if you produce 10,000 cards, you're going to plug into the formula your cost. So your average cost per card, that's what the C bar means. This means average over there, the mean or average. So the average cost per card is going to be 0.5 times how much? Times 10,000, right? But your initial setup costs remain the same, right? 5,000 over 10,000, and if you do that, you get what's that? 5,000 plus 5,000, right? Over 10,000, which is how much? $1. Okay, just $1 per card if you produce 10,000. So notice how your cost per card goes way, way down, right? If you produce a lot. Okay, 100,000. I'm not sure what it comes out to be, but there's a limit. Okay, to how much, like it's not gonna ever cut to zero, right, to produce the card. What's the limiting value of producing, what is the limit of C bar as x equals to infinity? How can I use what I just learned about limits to figure out the answer?
Yeah.
What did you say? 0.5, why? That's right. Very good, because the degree of these two terms is the same, right? So I compare their coefficients, so if I plug in a huge number in here, right, my limit, right, of C bar as x goes to infinity is going to be equal to 0.5. So eventually, my cost, if I produce a whole bunch, is only going to be 50 cents, right? So if I'm charging 52 cents per card, I'm going to make a profit, right? But if you only sell 100 cards and you're charging 50 cents per card, you're going to lose money, right? Okay, so that's why, Costco, Walmart, all those companies pay, Amazon, who else? I don't know, Lamborghini. They sell a lot of Lamborghinis. I have 7. What?
Can I get that instead of 1, 2,
7 Lamborghini, what?
Can I get the Lamborghini instead of 1, 2, 2,
Oh, sure. Okay, so that's kind of real. So limits of sequences that converge. Examples of sequences. So a sequence, as you might know, or if you might remember from last semester, is just an ordered set of numbers that's doing something special. So like a sequence is 3, 5, 7, 9, 11. This is called a diverging sequence, meaning the numbers never reach a limit, okay? So if a sequence reaches a limit, if it's not diverging, it's convergent, okay? Very good, which means it reaches some set value after a long period of time, okay? So another example of a sequence, -1, +1, or not plus, yeah, -1, comma, +1, -1, +1, -1. Do you think this sequence converges or diverges or neither? Yeah, it doesn't converge, right? Because it doesn't converge because it's bouncing, right? First it'd be -1, then 1, then it never really reaches a set value. This one is converging. Let me look at my notes, okay? Converging sequence would be something like 1/2, 1/3, 1/4, 1/5, ... This one has a limit. Can anyone tell me what that is eventually going to hit? 0. How come? Because it keeps getting smaller and smaller and smaller. It doesn't always reach 0. It can reach other values. Okay? But so this converges. We'll do another one in a second. This one. Okay? And let's see if I have this on my PowerPoint somewhere. It says if a sequence does not converge, it diverges. And then it says this. Okay? So what this says is that if a sequence converges, okay, then the limiting value of that sequence is the same as the limit of the nth term. Okay? So in that last one, I'll show you what I mean in a second. Okay? So in that last one that I just had, where it went 1/2, 1/3, 1/4, 1/5, and I think of this as n equals 1, 2, 3, 4. How could I write the a sub nth term? What's the a sub 1 over? Very good. Do you guys see where Mitch got that from? 1 over n plus 1? Because 4, I have a 5 down here, so this is always going to be n plus 1. So what this says is that the limiting value of the sequence is going to be the same as the limit as n approaches infinity of the nth term. So if I take the limit as n goes to infinity of 1 over n plus 1, what's that equal to? As this gets very large, this is equal to 0. Got it? You got that? Let's try 2 more, and then we'll try one that's a little trickier, and then we'll try one that's kind of trickier still. Okay? So say I have, and these look very scary, but they're not. Okay, so say I have 3 halves, comma 6 fifths, comma 9 tenths, comma 12 seventeenths, comma dot dot dot. Find 12. What did I write? Oh, I want to write 12 seventeenths. Okay, 12 seventeenths. And they say find the limit of the sequence. Find the limit of the sequence. So this is different than a series, okay? Next year, for those of you who take Calculus BC, you learn how to find the limits of series. Series are when you add all those numbers together, okay? This is just finding the limiting value, the end value, because series, that's like second semester in Calc BC, and it's like there's all these formulas that you kind of have to memorize and stuff, but right now we're just finding the limit of the sequence. Yes? Recursive, meaning it depends on the previous term? What do you mean recursive?
I meant that change the so 2 to 5, 3 to 5 to 5 to 10. 2 to 5 doesn't matter. Does that matter?
Yeah, it matters. It matters. I mean, you have to figure out what the formula is. And this one's kind of tricky to figure out the formula. So what I always do, I put n equals 1, 2, 3, 4 up here, and then I'll say, okay, so what would be the nth term? So how is this number on the top related to the bottom number?
3n.
Top is 3n. Very good, Dan. Anyone figure out the bottom number? Get it, got it?
N squared plus 1.
Very nice. Okay? So the bottom is just n squared plus 1. Alright? You guys see that? I mean, it's just, how do you do that? I think you just have to look at it. Or you know it's a quadrat. If it's going up by odd numbers, increasing. If it's going up by increasing numbers, like you said, Mitch, usually it's going to be a quadratic. Okay? So it's going up by 3, then by 5. So this is quadratic on the bottom, but it's not a factorable quadratic, but it makes it tricky. So then all you have to do is find the limit as n goes to infinity, right, of 3n over n squared plus 1. What's that limit equal to?
0.
0, right? It's not, the answer isn't always 0, and I'm going to show you that in a minute, okay? So this one goes to 0 because the degree of the bottom is bigger than the degree of the top, right? Can you see that? Okay, so let's do one more that looks really scary, but it's not all that scary, okay? So find the, do you need more time to write that down? You're okay? Find the limit of, as n goes to infinity, C of n, if of C of n, C sub n, if C sub n is equal to 6 over n to the 4th, big bracket, n squared, n plus 1 squared over 4. And you go, oh my God, what is that? And this is it's a way to generate a unique sequence. But all you really have to do is, well, who can tell me what this is without Francisco knows? What's the answer?
I don't know, where is it squared?
It's gonna be 3x. And so, how do you figure that out, Jack?
So you just, first thing you like square the n plus 1, and you get like,
That's what that meant to do.
you get like n squared plus something weird.
Right,
And then you multiply the n squared times that, and you get n to the 4th.
right,
And then you multiply 6 over n to the 4th across the whole thing.
uh-huh,
And you get 4n to the 4th times 6n to the 4th over 4n to the 4th. And then you use one of the outputs.
yeah. So, like, you don't even have to multiply it all together, right? If you did multiply this all together, you would get 6 times, so on the top you'd have 6 n squared, right? And this, when I FOIL it out, is n squared plus 2n plus 1, right? So over 4n to the 4th, right? And then if I kept multiplying that out, this becomes 6n to the 4th plus 12n to the 3, right? 12n cubed plus 6n squared, right? Over 4n to the 4th. But all I really have to do is look at these two terms, right? Because the coefficients, the exponents, are the same, and the coefficient, the ratio of the coefficients is 6 to 2, right? So this is going to approach 6 to 2, 6 to 4. Sorry, oh, look at how I made that in, which is equal to 3 over 2. Now, if I just looked at this, I can do it. I can say, well, I know that my highest degree term is going to be the 4th power, right? And there's going to be a 6 in front of it. And I don't have to worry about what's happening here and what's happening here, because this doesn't matter, you see, because they're lower degree terms. And so the only thing I really have to worry about is the 2 highest degree terms. And so I know my highest degree term here is going to be 6n to the 4th after I multiply it all out. And I know my highest degree term down here is going to be 4n to the 4th. So all I really have to do is look at those two numbers, and I get that my limit is 6 over 4, which is 3 over 2. Question? Great? Isn't that amazing? I thought you would think so. Brooke thinks that's amazing. No one thinks it's Daniel doesn't think it's okay. Well, in that case, if you don't think this is amazing, we're going to send you on find the limit of the following sequences. Homework. There it is.
You used to watch Toy Story?
What? You want to watch Toy Story now? We're done. Okay. Okay, you can start. You got it? I didn't talk to you. All right. Oh, I didn't give you back your quizzes? Okay.
Let me pause.